Last time we were together, we worked through a problem dealing with specific heat. And when we did so, we only looked at a calculation that involved one substance, and that's it. So, right now, we're going to do a second specific heat calculation, but this time looking at heat transfer as it goes from one object to another. If you look here, what we have is some water, and we also have some aluminum metal. So right here is 10 milliliters of H2O, and sitting right next to it, this is a pile of aluminum metal, and specifically it's 3.90 grams of aluminum. Essentially, what they're telling us is happening in this problem is this aluminum is pretty hot. It's at a temperature of 99.3 degrees Celsius, and we're going to call that the initial temperature of the aluminum metal. The water, on the other hand, also has its own initial temperature. It's 22.6 degrees Celsius, and we're going to call that TIW. Again, because its initial temperature is different than the aluminum. And essentially, what's taking place in this problem is that we're being asked to take all of that aluminum metal and transfer it into the water. And we're supposed to figure out what's the final temperature going to be after we do that. And there are a couple of things to note in this particular problem. Number one is that it's clear that the water will heat up, right? Because you're adding this hot aluminum to it. And it's also clear that the aluminum will cool down because you're putting it into some cool water. What might not be obvious, but is super important, is that the final temperature, which is what we're being asked to solve for in this particular case, is going to be the same for both of them. So I don't need to label TF as for aluminum or for water because they're essentially going to come to the same final temperature. Okay? So this is a complex problem. We can set it up as essentially two separate problems at first. One where we look at heat that the water gains, and two where we look at the heat that the aluminum loses. Okay, so for each one of these, we need a mass. For each one of these, we need a specific heat. And for each one of these, we have a delta T. That delta T is going to contain some components that are the same, but a couple of components that are a little bit different as well. So let's talk through it. If I wanted to calculate QW, the mass of the water, I've got to note one thing that is really important and is given in the problem, that the density of water is 1 gram per milliliter. Well, they tell us we have 10 milliliters, so that 10 milliliters is actually equal to 10 grams. This really only works for water because water's density is 1 gram per milliliter. One thing that was not given in the problem for us was the specific heat of water. Generally, I would have students memorize this. It's 4.184 joules per gram degree Celsius, and that's a pretty high specific heat. And then finally, for water, we would say delta T is the final temperature minus the initial temperature. And in this case, The initial temperature of the water is 22.6 degrees Celsius. Now, I could do the same thing with the aluminum. I could say QAL is equal to 3.90 grams. The specific heat of aluminum is given to me. It's 0.903 joules per gram degree Celsius. And the change in temperature is going to be final temperature minus the initial temperature, 99.3 degrees Celsius. Now, here's the key to getting this problem right. It's a huge kind of conceptual piece that you have to understand. One of these things is losing energy, heat energy. That's the aluminum as it cools down. But the other is gaining heat energy. And the assumption that we make is that all of the energy that is lost by the aluminum is going to be gained by the water. Okay, so mathematically, we put a negative sign in front of the aluminum, it's losing energy. We put a positive sign in front of water because it's gaining energy. So we end up with a setup that looks something like this: negative 3.90 times 0.903 times TF minus 99.3 is equal to the Q of water, which is 10 grams times 4.184 times TF minus 22.6. All right, I'm really out of space, and so if you don't forgive me on this, I'm going to go back and erase a few things so I can have some room to work this out. It really just becomes an algebra problem though now. All I have to do is solve the setup that I just put up there. So the first thing I'm going to do is multiply terms together on the left hand and the right hand side. So I'm going to say negative 3.90 times 0.903. What that gives me is negative 3.52 times TF minus 99.3. And that's equal to, I'm going to do the same thing on the other side, 10 times 4.184. That's 41.84 TF minus 22.6. Now I just have to distribute just like I would in math class. So I'm going to say negative 3.52 TF, and then negative 3.52 times negative 99.3 equals a positive 322.7. I'm not really paying attention to significant digits here like I should. I want to keep a couple of extra digits just to make it look clean. I'm going to do the same thing on the other side. And so I'm going to say 41.84 times negative 22.6 equals negative 945.6 degrees Celsius. Now I'm going to put like terms together. So I think the easiest way to do that is on this left-hand side, let's add 3.52 TF to both sides. So I'm adding it here as well. And then let's also, at the same time, let's add 945.6 to both sides. Should probably do that in 2 steps, but I hope you're with me. So on the right side, I'm going to get 41.84 plus 3.52, get 45.36 TF. And on the left side, I get 322.7 plus 945.6, and that is 1268.3. Okay. The final step, all I have to do is now go through and divide by 45.36. Divide both sides by that. So if I say on my calculator 1268.3 divided by 45.36, I get 27.9. It's really 28.0 degrees Celsius, and that's my final temperature. There are a couple of things that I want to conclude with before we leave. Number one is, in any of these problems, your answer should always be between your two starting temperatures, always. The second thing I want you to note is that our final temperature of 28 degrees Celsius is much closer to our initial temperature of water than it is to our initial temperature of aluminum. That makes sense to me. Here's why. Water has a very high specific heat, so it takes a lot of energy to heat it up. And aluminum has a low specific heat, so it loses energy very rapidly, very quickly. So it makes sense that the aluminum is going to cool significantly, but the water's only slightly going to increase its temperature. Okay, let's come back together and we'll have you guys try one of these on your own.